So, well, this is, if you like, the technical point, but it's interesting to see that this one is trivial to verify, but it's equivalent to the fact that the reflection preserves products, which is a little bit harder to compute if you have to do a lot of equivalence relation checking and so forth. When you collapse, you have to impose the congruence relation. It's the congruence relation that's generated. Anyway, this is technically useful because if you wanted to define the t-topos associated to a space, that is to an object in a cohesive topos, try to mimic the classical constructions from a space, finding the little topos. This one of the steps should involve, I think, this reflection. Forcing the site, given the site, slash it by a given x, that's another category of the same type. I mean, yeah, this is equally important. Not only have this closure property, but if you have a discrete vibration over something, discrete vibration, and the base is in one of these categories, subcategories, then so is the total space. And this localization, of course, is a discrete vibration. So, yeah, that's such a program. That's an equally important closure problem. At the moment, I'm considering these classes as candidates for generalized space, you see, so these are properties that they should have. Well, I got to thinking, well, really, this is sort of complicated. There's something that this obviously implies, even more general than any of these, but still very restrictive and applicable to all the examples. So that's a good kind of thing, right? It's simpler, more general, and yet it includes all the examples. What could be better? Anyway, so that's what today I'm giving it the fanciful name empty. Now, what I mean is this. An object, it's about idempotence. An idempotent, of course, is an endomap whose square is equal to itself. And I want the axiom which says this equals 1 sub A. So I'm calling A an empty object if it has no idempotence. The colloquial use of the negation no, is not the one that logicians use. It simply means it implies a trivial case. Instead of implying false, it's implying a trivial case. So it's a well established to call this no idempotence. So an object that has no idempotence, you see, in particular, it means it has no global points. So suppose you had a terminal object and a global point. Well, of course, the unique map here, followed by that, and the point gives rise to an idempotent. Thank you. Of course, in a category with a terminal object, a point in the most narrow sense of point, i.e. a map from 1, trivially gives rise to an idempotent. So if A is empty, it doesn't have any points in particular, but it doesn't have any degeneracies. A better way to think of it, perhaps, is, a general map in a category I sometimes call a figure. This terminology for later as well. Figure of shape A in the space X. And this is slightly more than just another name for map because I require that, well, let's just say it this way. This is a script A figure if A is an A, where in principle A is just some class of objects, later to be specified. But so a figure, there's a terminology which I will take over from topology, again, simplicial sets, the 1950. You talk about degeneracies. A degenerate figure is one such that there exists an idempotent, which leaves it fixed. Degenerate. Well, I mean, in other words, it's really degenerate if he's not one. So this degeneracy of this is the very clear geometric, ancient geometric usage. The shape of a triangle, for example, might have a singular realization. A figure is called singular if it's not a monomorphism, just to mean singular is general. But the very special kind of singular is to be degenerate, i.e. to be a monomorphism in the sense that it factors through a non-trivial idempotent. That's the sort of thing, if you have a triangle in X, means a figure of shape, a generic triangle, yes, but that shape might be degenerate and the triangle really collapsed to a line. The idea of collapsing a triangle to a line. Or a degenerate path could just be a point. Or even a path which happens to be a closed path is degenerate to the extent that, well, is that right? Yes. So this particular way that the idea is that any of these toposes of generalized spaces of a certain, any topos which represents a generalized space in the sense that this generalized space is parameterizing discrete sets. Okay, I didn't say that, but that's the idea of what these petite toposes are. Discrete spaces parameterized smoothly by something, and the something could be a group, it could be a classical space, it could be an étal space, but among those there will exist an adequate family of figures with no degeneracies. Right, so you have G sets generated by a group. Group doesn't have any idempotents. Po-set, well, there aren't even any endomorphisms, let alone idempotents in the po-set itself. But it's true for even the most general thing that I've mentioned, that though there might be endomorphisms, there are no idempotent ones. Okay. So this very simple condition that there should be a site consists of empty objects, i.e. objects that have no retracts. And hence no figure is really degenerate. No degenerate figures. Because if there's no way to degenerate them and the figures are those kind of objects, then there are no degenerate figures. So that seems to be the most general notion of. So we can add that to the list. Because trivially, it's easy to see that this again has these two properties. If I take a category with no idempotence, raise it to any power, it still has no idempotence. Because the maps, the natural transformations in a functor category are basically calculated in the values, and the values have this restriction. And again, same with discrete fibration. The maps, the discrete fibration are labeled by the maps below, and they compose that way. So if there's no idempotence below, there's certainly no idempotence above. And so there's a reflection. In other words, here's the problem for computing. You could take any small category, even say a finite category, force it to have no idempotence in a universal way. How do you calculate that? In principle, it's clear that it exists. But what is it in a concrete case? Because it's very, I guess, kind of hard to understand how the calculation should go. To generate, you have to generate an equivalence relation, to generate a congruence relation on the category, starting from the fact that any idempotent and the identity have to be identified, and you have to close under composition. Making those identifications, you might have created more idempotents, so it sounds like you have to go through a sequential construction. Now, there are some examples where it becomes easier, but still not obvious. I'm not saying it's hard, it's just that they don't know how to do it. Maybe someone can figure out. I hope someone will figure out how to compute the idempotent reflection of the given. There are a lot of categories in which you have, it's the same as inverting split. You can sort of, without loss of generality, always assume that a category has split of idempotence. Any idempotent splits into an epi followed by a mono. You could explain the idea of degeneracy in terms of that instead, for example, maybe more effectively. It would mean, you see, that the figure itself factors through that quotient. Or is it? What am I saying? So there are many categories that have pullbacks, and if you take a split epimorphism, any pullback of it is always a split epimorphism again. So if you have split idempotence and you have pullbacks, you don't even have to assume any exactness properties about the pullbacks, because they're automatically true for idempotence and for split epis. Pulling back to a general epi might not be epi, but for a split one, yes. So if you have pullbacks and split idempotence, then every fraction, you see, the maps in the category we're trying to construct could be called like fractions, because you go ahead, but then whenever you have an idempotent, you can also go backward, or whenever you have a split epi, you can also go backward. So it's sort of like a fraction. But in principle, fractions are words: A, B inverse, C, D inverse, and so on. Right? But in case your category has pullbacks, all fractions can be reduced to length 2, because if something followed, an arbitrary thing followed by a split epi is equivalent, is in fact a split epi followed by something, and so all fractions can be reduced to length 2. Something like the calculus of fractions used in homotopy theory and so forth, and it's in one way simpler, but it's more explicit. But on the other hand, at least at this moment, less clear how you complete it. But anyway, the associated T topos could perhaps be described